Interval notation, here we have the first two done. This is to remind you of how this looks. We have a is less than x is less than b is parenthesis a comma b. Less than or equal to x less than or equal to b is bracket. How would it be if it's a less than x less than or equal to b? It'll be ab parenthesis on the a, bracket on the b. Similarly, on the next one it'll be a b. Now here we'll have parenthesis a comma, where does it stop? It doesn't, so it's going to infinity. Now can we put a parenthesis or a bracket, can we put either one for infinity? No, because a bracket means that it's going to be equal to, but a parenthesis says it's not equal to. Similarly on this next one, x is greater than or equal to a. You have to be careful there and not just go into automatic mode. It's greater than or equal to a, so it's a comma infinity as well. It doesn't say less than. Now take a look at what I did on this one. I made it darker. I think that one's still pretty clear, but sometimes I see students do this. Both parenthesis and bracket means neither. So if it's not clearly one or the other, you haven't done it. So make sure that it's either a bracket or a parenthesis. And this last one's any real number. We're going from negative infinity to infinity with parentheses. Now let's take a look. Is this a bounded interval? Is there an upper bound and a lower bound? Yes. Similarly on number 2 or 2i there is. And the same thing on 3 and the fourth one. Now what about the fifth one? Is it bounded? If you had to say just bounded, you would say no, but we can call this bounded below. And similarly, since this is basically the same, it is bounded below. And the last one is just unbounded. A function. For every element in the domain, values of the independent variable, there is exactly one member in the range, values of the dependent variable. Domain, all values of the independent variable, i.e. x values. Range, all values of the dependent variable, i.e. y values, is what we typically deal with. Since this is all review, I'm going to go through it fairly quickly. Odd-even functions and symmetry. Given a function y equals f of x, an even function is defined as f of negative x equals f of x. So that means if I plug in a negative x or I plug in a positive x, I get the exact same y value. So if here's my point xy, then negative xy would be over here. So that's going to be symmetric about the y-axis. If we have a point xy, this time if you plug in negative x, you get negative of the y value. So if I have a negative x, it's going to be negative of the y value. This will be negative x comma negative y, and this will be symmetric about with respect to the origin. Let's look at an example, and when we come back, the next problem after these, I'll do the odd-even. And that will be important for what you're going to need to write. Find the domain. There's two ways to find domain. You either find the values that do work, or you find the values that don't work, and it depends on the problem. In this case, what we're going to do is we're going to look at the values that don't work, because there's only going to be one. X minus 2 cannot equal 0, so x cannot equal 2. What would that domain be? We're going to write it in interval notation. Negative infinity to 2, parenthesis, union with 2 to infinity. And that's it. Now domain is a lot easier to do than range. Range is going to take us some work, and we're going to have to kind of think about it. And I'm going to start right now giving you an idea that we're going to use extensively. So we know that 2 is a key value. Let's look at what happens as x goes to 2 from the right side. We're going to look at a table here. So what kind of numbers are going to go to 2 but from the right side of 2? And you can think of a number line, 1, 2, 3. The numbers to the right of 2 but close to it, we can pick a number like 2.1, 2.01, 2.001. Now you could use a calculator, but these ones aren't particularly difficult. 2.1 minus 2 would be 0.1. 3 divided by 0.1 would be 30. On this one, 2.01 minus 2, 0.01. 3 divided by 0.01 would be, move it twice, 300. This would be 3,000. Those numbers are getting big. Let's look as x goes to 2 from the left side. This time we'll use numbers close to 2 but coming in from the left, 1.9, 1.99, 1.999. No, I'll skip the 1.91. 1.99 minus 2 would be negative 0.01, so that will be negative 300. Similarly, this will be negative 3,000. So it seems like as we're going to 2 from the right side, these numbers are getting really big, going to infinity. On the left side, it's going to negative infinity. Now sometimes people make the false conclusion saying, oh, it's all numbers then. Not exactly. Let's take a look and see what's happening as x goes to infinity. So on something like this, we want to start plugging in some bigger numbers. For example, 1,000, 1,000,000, 1,000,000,000. What's happening to these numbers? This is going to be 0.003 approximately. If you did it on your calculator, you'd have 01 after that. And this is getting closer. So we have 0.1, 2, 3, 4, 5, 3. They seem to be going towards 0. Let's look at the other side, going to negative infinity. So this time we would have negative 10 to the third and negative 10 to the sixth. And what are those going to give? This is going to be approximately negative 0.003 as well, and approximately negative 0.00003. Now, will it ever hit 0? Let's take a look at this equation. What would have to happen in order for a fraction to equal 0? You would have to have the top part equaling 0. So while as x gets big, either positive or negative, the values are going to go to 0, but they'll never exactly equal 0 because we don't actually reach there. So what this is telling us is that y cannot equal 0, and we could write that in our notation as negative infinity comma 0 union with 0 comma infinity. That would be our range. Let's take a look at this one. On the problem number 2, we looked at the numbers that don't work. On problem number 3, we're going to look at the numbers that do work. What do we want in this problem? We only can find the square root of numbers that are greater than or equal to 0. So let's take that inside part and make it, oh, I already started writing the inequality. Minus 6 is greater than or equal to 0. How do we solve this? Try to think about that. Hit pause. Come back. Alright, the way we want to solve this is using the number line. So we're going to go factor this out, x minus 3 times x plus 2. Be careful about that factoring. A lot of people make mistakes when it's negative 6 there. We'll set up a number line. We plot our zeros of this. They'll be at negative 2 and 3. X. Now we could either plug in a number in every single interval, or we can sketch the graph. In this type, if you're dealing with a polynomial, you should be sketching the graph. This is a simple polynomial. It's a quadratic, so it's a parabola that opens up. Just put a dotted. This is plus because it's above the axis. This is minus because it's below, and then positive again. Now what kind of numbers can we deal with here? We want those numbers that are less than or equal to 2 or greater than or equal to 3. And if I write that in interval notation, it'd be negative infinity to negative 2 bracket union with 3 to infinity. Now this is a lot harder to do for your range values. Now what did we do on this first one? We looked and said, what's happening as we get close to the 2? We're going to do the same thing here. If I say, due to symmetry of the quadratic, you know it has an axis of symmetry. What we can do is we can focus on just the one side. Let's go to 3 from the right side. What happens to those numbers? The y value, I'm not going to write this one down though, you can just think about that. You're plugging in 3. This number is, you're getting close to 3. This number is getting close to 0, and this is getting close to 5. Well, that's going to give us 0. As we go to, one thing I didn't point out there, this was getting close to 0, but there were positive numbers. If we go to 3 from the left side, so example 2.9, 2.99, this is going to be a negative number times a number that's going to go close to 5, but we're really looking at the square root of that. So you have a negative times a positive gives us a negative, so that is imaginary or undefined. There is no value there. So this thing is going to go down to 0 definitely. We know it's a square root. It can't go any lower than 0. What happens as you go to infinity? Well, if you take a huge number, square it, and then minus a number and minus 6, when you're saying minus the x and minus 6, after you've squared that, it really is not having much effect. You can think of like a million, 10 to the 6. You square that, you get 10 to the 12th. Well, if you subtract a million, it's subtracting very much money. And then the 6 is having a little effect. And what's the square root of that? It's going to infinity as well. You can also look at going to negative infinity, and that behaves in the exact same way. So what's the range on this one? The smallest value was 0, and it goes up to infinity. One thing I didn't do it for either of these, I didn't sketch the graphs. Let's take a look at what this graph looks like, and the graph could have helped us to deal with the domain and range as well. This parent graph, the basic function graph that you learned last year, would have been y equals 1 over x. But it's shifted 2 units to the right, because that's what would make this value 0. And the 3 means it's being stretched out. So we have a 2 there, and that is our function here. Now that number 3 is not a typical function for you to deal with, so that one's not going to be as easy to do. But let's see, we know it's going to go to 0 when x is coming to 3 from the right side, and we know it's going to get really big. In fact, we were talking about this having little effect when it gets really big. So what's the square root of x squared looking like? I'm going to talk about that a little bit more. That is going to start off with a curve, and then it's going to end up looking a lot like x on this case. And by symmetry, we could say the same thing. This is going to come in, and it's going to look like that. If you zoomed out enough, it would look like the absolute value graph. Alright, state if this function is odd, even, or neither. The book is going to tell you when you do your homework that just look at it. Well, I'm going to tell you to do that too. Just guess first. Then what I want you to do is do the same thing on your homework. I want you to find it, show it. You need to be able to plug those things in and do that work. So make your guess for all of these. They all have x squared in there in some place. To prove it, we're going to plug in negative x. So we plug in negative x, square that. That simplifies to x squared. That is the exact same as our original, that's f of x. Therefore this is even. And I know this one's a pretty straightforward one. These two, some people can make mistakes on them. Let's try this one. F of negative x equals negative x quantity squared plus 2, x squared plus 2. Again, that's f of x, so it's even. Write that down, actually equals f of x. Let's plug in for the last one here, and we'll have negative x plus 2 quantity squared. Well, there's nothing we can do to get that negative out there and make it positive. That's not going to equal the opposite, nor does it equal the exact same thing, so this is neither. Let's look at a couple more examples. We have f of x equals x cubed. Again, make a guess as what you think on there. So we have negative x. We'll plug this in, and we have negative x quantity cubed. So we get negative x cubed. Well, our function's x cubed, and this is the negative of it, so it's negative of f of x. Therefore, it is odd. Do the same thing on this one. Negative x cubed plus 1. We have negative x cubed plus 1. Well, that 1 is not the exact opposite sign, and this isn't the same as the original, so this is also neither. Write a formula that expresses the area of a circle as a function of its diameter. Well, how are we going to do this? We can start with, we know the area of a circle is pi r squared. So we have it as a function of its radius, but we don't have it as a function of its diameter. So somehow we need to get rid of the radius, and then we need to get in the diameter. So that leads us to ask, can we find an equation that relates the radius to the diameter? Yes, we can. The radius equals the diameter over 2, or you could have started with the diameter equals 2 times the radius and then solve for r. Now we can say the area in terms of the diameter alone is going to be pi times d over 2, because that's what our radius is, quantity squared, and that can be simplified to pi over 4 times d squared.